Okay, so we'd like to welcome Kenny DeComer from
VUB.
from the VUB in Brussels. And yeah.
Okay, so thanks, Ray, for giving me the opportunity to speak here. So it will be about some joint work with my student, Joel Zokutala. So I say partly joint because we basically together did some work on this, some much more detailed work on this in rank 1. So think of quantizing SL2R. But here I would like to paint a more general picture of how to quantize general connected linear semi-simple Lie groups. So let me be a bit more precise in what I mean by this. So if I have L, so this will be one of these objects, a connected linear semi-simple real Lie group. So I'll explain what this means in a moment with Lie algebra L. So you can think of following examples. So you can think of SL and R. You can think of some group of automorphisms of some indefinite quadratic form over the reals. And then because I want to have something which is topologically connected, I have to take, in most instances, some connected component at the unit. You can think of SL and C. You can think of SU and. So these are all examples of these objects. So the point is that this real just means I will be considering general Lie groups, not just complex Lie groups or compact Lie groups. Connected, I already said, is just a topological condition of being a connected Lie group. The fact that it's semi-simple just means that the associated Lie algebra is going to be semi-simple. So direct sum of simple Lie algebras, ones which are not abelian and don't have any non-trivial ideals. And then the last point is that I will only work with linear Lie groups, which means they are the ones which can be embedded into GLNC for some n as a closed Lie subgroup. And here I can actually choose the embedding such that L is globally stable under the usual transpose adjoint under the complex transpose map. So these are the objects I will be working with. And so associated to such a Lie group, we have a C-star algebra. So let's C star L V. So we have an associated C-star algebra, the universal group C-star algebra of L. And then this group C-star algebra has some extra structure. So there's something which is the co-multiplication map. It will be a map from C star L to the tensor product of C star L with itself, except that there's some small technical detail we actually need to put here. Multipliers. I will not explain things about multipliers because it will not be essential for this talk, but you can simply think of the diagonal map. So if I have not inside this one, but inside multipliers, I can think of unitary generators given by shifts by group elements. These will be sent to this. And then the point is that somehow together, the C-star algebra together with this coproduct, you can recover the group. And so it gives a one-to-one correspondence between groups and certain C-star algebras. And second condition, which actually follows from the first, is that the representation category of this C-star algebra, so representations of the C-star algebra non-degenerate on Hilbert spaces is actually monoidal. So the point is that this C-star algebra basically encodes completely the representation theory of your Lie group. So looking at representations of this C-star algebra or looking at unitary representations of the Lie group L, continuous, strongly continuous representations unitary of this Lie group L, it's the same thing. And of course, you know how to tensor representations of L. And then by this more abstract formalism of using the coproducts, you can actually also directly encode tensoring representations here to tensoring representations here. Take two representations, and then I get a new representation, apply co-multiplication, apply first representation to first leg, second representation to second leg. And so this is a very general way of multiplying representations once you have a map like this. So what is the goal? Well, we basically are interested in deforming such structures. So I will not be very detailed in this talk about what I mean precisely with quantizing, because that would take a bit more time. But the question is basically if we have some way of perturbing the C-star algebra into a family of C-star algebras labeled by some real number Q. So the question is, do we have for such an L a family of C-star algebras, C-star Q of L, such that they are still they still have some kind of coproduct in this way, and such that still their representation category. So let me put the Q here, and then here I can put the Q there, and so that representation category is still monoidal. So this is kind of like the goal that we are after. And the deformation basically means that in some sense, which I will not make precise, is that if we take the limit of Q goes to 1, we find back the original group C-star algebra. And so this was kind of an open problem for a long time, how to, if it is possible to do such a thing, and there were some results in rank 1, which turned out to be highly non-trivial and wouldn't really work directly on the nose for these Lie groups. You had to do some non-trivial operation to make it work. And it was kind of very hard to see how to do it in general rank. So this new construction that we came up with will basically work in arbitrary rank and in a very general way with a highly structured way of producing these quantizations, except that there is a negative answer to the first question, but not a negative answer to the second question. So this is the surprise of the construction. If I can find my red chalk. So the question, do we have associated C-star algebra here? Yes, this we can make. Do we have a coproduct? No, in general. But do we have a monoidal structure? Yes, in general. So I'll try to see, hopefully I will have time by the end to explain why there is still a monoidal structure, even though we can't quantize the co-multiplication. But I should say here in general, there are some cases where you can actually produce what is called a quantum group associated to L. Namely, for example, if you take here compact Lie groups, then it will work. Then there's a very nice quantization procedure that you can do, basically due to Drinfeld and Jimbo, and then put in the analytic framework by the technology of Aronowitz, you can quantize these Lie groups. And then by some general procedure, which I will actually explain later, you can also do it for these ones, which are the complex Lie groups. So if you're compact or complex, we already knew this was possible with a positive answer to 1. And now I'm saying to you that also for the other ones here, you will be able to produce a monoidal category, even though in those cases, it will not be possible to create coproducts. So this is what I hope to explain to you in the rest of this talk. So I will actually not say very much about C-star algebras because mostly I will be telling you how to construct an algebra associated to L, actually to the Lie algebra of L. So I will be making not a C-star algebra, group C-star algebra of L, but a deformation of the universal enveloping algebra of the Lie algebra L. This will be the most part, the largest part of the talk. And then I hope I have some time at the end to say how to pass to the C-star level. So let me say some things about what goes into the construction. So we will need a little bit of structure theory for such real semi-simple Lie groups. So I will draw what is known as a Cartan square. So I will start with L and I will construct some associated Lie groups. And similarly, on the level of the Lie algebras, I will construct from my given real Lie algebra L some associated other Lie algebras. So the first step is that I will complexify. So associated to G, I automatically get a complex Lie algebra just by taking L and complexifying. And it turns out that there is a kind of universal largest integrated version of small g I can take, which will contain L. So this is kind of like some universal complexification. So this G integrates to G, which will be complex, semi-simple, connected, and in a sense, a universal one, so largest as possible. Now, this G, being a Lie group, semi-simple Lie group, will actually have a maximal compact subgroup, U. Now, this U, I have to choose one. So I can choose one and then all other ones are conjugate to this one. But the problem is I want to have compatibility of this one with this one. So I can't just choose it completely arbitrary. So what I do is I choose it in such a way that if I look at the associated Lie algebra, it behaves well with respect to the other Lie subalgebra L of G. Namely, it will be the direct sum of the part which lives in L and the part which lives in UL. And it turns out that you can always do this. You can always choose U in such a way that you have compatibility in this way. And once I have constructed a suitable U satisfying this condition, I can complete my square by looking at the intersection of L and U. So this U will now be a compact, semi-simple connected Lie group. And the intersection will still be, of course, compact, connected. So it will be compact, of course. Connected requires a little bit more work to see. But what you have to be careful is that it's no longer semi-simple in general. So it's a little bit more general. So since I already said compact, I don't really need to say this, but let me just put it for emphasis that it's reductive, meaning that there could be some abelian components in the decomposition of the Lie algebra. So this is something that, so you can't keep the semi-simplicity for the maximal compact subgroup, but you can describe precisely those cases for which this will not be semi-simple. So these are what are the ones which are related to the what are called Hermitian symmetric spaces. And so this is maybe something I should say here. So this Cartan square basically encodes the duality that you have between real Lie groups and Cartan pairs. So inclusions of Lie groups, compact Lie groups of a certain type, which basically encode some geometric data. So if you look at the homogeneous space of U by the subgroup, these are precisely what are called the symmetric spaces of compact type. So I won't go into detail about what that means precisely, but just for those who know those already, these are the things that you get. So the Riemannian symmetric spaces of compact type. Okay. So the point will basically be to construct my quantization using this input data. So before I continue with the quantizations, let me first say some more things about this diagram. So let me first complete it here on the Lie algebra level. So this is just the intersection of L and U. So one handy way to encode the different real forms of G that I get here. So this is a real form of G because its complexification is G. This is a real form of G because its complexification is also G. One way to encode such real forms is by star structures, which is a nice way to immediately relate it to star algebras and C-star algebras. If I put this board down, nobody can see it probably. So. Okay, well, I'll just leave it like this and then continue here. So note the real Lie algebra L can be encoded as a Lie star algebra structure on G. So the point is that I have G is given as L plus IL. And so I will construct a star structure on G, which will take an element X in L and send it to minus X, and an element in IL I will send to itself. So what do I mean by a star structure in general? It just means the usual thing that you expect of a star, so that this is antilinear, involutive, and it changes the order of the multiplication. And then it's really easy to see that you actually have a one-to-one correspondence between complex Lie algebras, which is your star structure, and real Lie algebras. So if I have a real Lie algebra, this is how I construct a Lie star algebra. If I have a complex Lie star algebra, I can create a real Lie algebra by just looking at all those x's for which x dagger is equal to minus x. So this is one star structure that I can get in my specific case from my non-compact real semisimple algebra L. And I can do the same thing for you. This is also a real form of G. So it also comes with an associated star structure, which now I will just write as star. So I have similarly U leads to G with some other star structure star, and then the compatibility of L and U that I had written down here, I can basically encode it as saying that star and dagger commute. And so I can write this as some involution theta of a complex involution of G, this composition. Right. So yeah, so when I want to make an infinitesimal version of this guy, what I will actually do is so infinitesimal version of my group C-star algebra? Well, I want to have a star algebra, so I will simply define it as the usual complex universal enveloping algebra of my complex Lie algebra G, and I will endow it with the star structure that I get from my real form L. So I can just extend anti-linearly as an anti-homomorphism my dagger to the whole algebra UG. This will give me a star algebra, and this star algebra in a way is kind of like an infinitesimal version of C star L. And also in classical representation theory, there's a very strong but very delicate link between representations of this guy and representations of this guy. So we expect also in quantum setting that this will still be true. So it's not only a technical step to first construct this one and then construct that one from it, it will also probably be very important for actually studying the representation theory of our quantizations. But I will not be talking about representation theory today. Okay, so the first step is to construct a quantization of our universal enveloping algebra here. And maybe I should say already at this point, so I will also have a coproduct that I want to deform. So if you look at the coproduct that I had here, and I kind of look at an infinitesimal version, then tensor product basically, so a product of two things becomes a sum of two things when I look at the infinitesimal level. So this one will actually be a Hopf-star algebra. Again, I won't recall or won't introduce what is a Hopf-star algebra. It just comes with some homomorphism into the tensor product of this guy with itself, given on generators by this formula. Okay. And so the idea will be that also on this infinitesimal level, I want to quantize, or I want to see if there is some quantization of this delta to a coproduct here. So it will not be there in general, but in the intermediate constructions, I will need this kind of datum. Okay, so let's start with quantizing stuff. So I'll start with quantizing my universal enveloping algebra of G itself. So for this, I pick some Cartan subalgebra of G and some Borel subalgebra of B. So again, if you are not familiar with these terms, just think of G as being SL and C, and then I will take B to be the upper triangular matrices inside, and I will take H to be the diagonal matrices inside. And then you can do this in general case as well. And so actually upper triangulars, I can split as a direct sum of diagonals and strictly upper triangular matrices. And this I can also do here. So I can actually write this in a very specific way as a direct sum of the Cartan and some nilpotent Lie algebra. Now, as I told you, this G, it comes with, I can choose for G some maximal compact subgroup, and then G will be the complexification of this maximal compact, of the Lie algebra of this maximal compact subgroup. This gives me a star, and I can always assume that my H is invariant under star. So we may assume that G has some compact real form. So let's say that this is the compact real form, which all compact real forms that you choose are basically equivalent, so it doesn't matter which one you pick. And then you can choose this datum such that it's compatible with this compact real form. So we may assume that H is basically stable under this star. So then, instead of looking at quantizing L, I will first try to quantize its compact real form. So as I told you, Drinfeld showed that on the compact level, there's no problem in quantizing things such that coproduct exists, and then automatically representation category is monoidal. And so if I look at the associated star algebra, universal enveloping algebra of G with its star structure, well, this universal enveloping algebra is a complex algebra which will contain the universal enveloping algebra of B, since that's a Lie subalgebra. And then this one will contain H. Now, the problem is that this one will not be compatible, that is to say, invariant under the star structure. So this one will not give you a star subalgebra, but then this one again will give you one. And that's basically saying I chose a maximal torus inside U. And so this will correspond to some maximal torus inside U, and then I have this inclusion here. So this is what I have classically. And what Drinfeld showed is that indeed, if I take any Q, and for me, because of analytical reasons, I always choose my Q real between 0 and 1, Drinfeld says, yes, you have some nice quantization of these structures. So everything basically exists on the quantum level. So just to give you an idea, if you haven't seen this before, of how this looks like, let me show you how the rank 1 situation looks like. So in rank 1, I look at U being SU2, and so G will be SL2C. So for example, if I look at UQ of SU2, so I need something corresponding to my Cartan part. This will be given by generators K, by a generator K, which is invertible, which is self-adjoint, and which is group-like in the sense that my coproduct will just be delta of K equal to K tensor K. And then I need to build a Borel part. So for this, I add some E corresponding to upper triangular, strictly upper triangular 2x2 matrix. So this one will satisfy commutation rule with K of the following form. And then I also need a coproduct. And here we see that coproduct is deformed. I won't get a symmetric coproduct like here. It will be perturbed by this K. So I'll have that. Yes, this is E tensor 1, but then I don't have 1 tensor E, but K tensor E. And finally, I need to complete UQG, and I need to have a star structure. So I can basically just add a new generator, which should be the star of E. But because of familiarity of symbols in the Lie algebra context, I will actually not use E star, but F, which is equal to E star K inverse. And then I will have the following relations. So KF K inverse is equal to Q minus 2F. And the important one is how this F commutes with E. And so the usual bracket of E and F, it will be some expression in K. And you interpret this by very formally viewing this Q as some kind of Q power of the usual generator H of SL2C. And so think of H as this matrix, and then K is somehow behaving as if it were Q to the H. And then you see indeed, if I have here Q to the H minus Q to the minus H over Q minus Q inverse, and I let Q go to 1 and apply power series, then indeed you get the usual relation, you know, for SL2C, that bracket of that commutator of EF is equal to H. So a very quick sketch of how these structures look like. So in this case, for compact structures, I can always quantize and get Hofstadter algebras, and everything is very nice. So what I want to stress is that when we did this quantization for U, so when we quantized the universal enveloping algebra, we picked already this datum here. So we picked the maximal Carton and we picked the Borel, and we really used this to make these Hopf algebras. You see it in this presentation of UQS U2. I presented by generators and relations. I have something belonging to my Carton. I have something belonging to my Borel. And then with those generators, I make my, with those generators and relations, I construct my Hofstadter algebra. So the point is that if I want to quantize stuff, if I want to quantize structures related to G, it somehow has to behave well with this choice. So if I want to quantize my L, I had better make sure that my L interacts in some nice way with this given datum. And it should also correspond well with my given compact structure. So that's now a lot to ask of my real Lie algebra L. And it turns out that you can always choose. So for L, we can always choose H such that also H dagger is H, so that H is globally preserved by the dagger. But here the problem is that not all choices are equivalent. So depending on the purpose that you want to have for this H, you have to choose a specific one. There's a finite class of ones that you can take. They can be in different positions with respect to this one. And the one that I will need for my quantization is called the Satake position, or the anisotropic position, or I also call it the minimally compact position. So let me just explain what I want of this position of L, or of this dagger. Basically, that's the same thing. So for our purposes, we want interaction of dagger star and our Carton datum as follows. So let me start with my complex Lie algebra G, but forget the complex structure. So I now will view it actually as a real Lie algebra. I can do that. I just forget something. It becomes a real Lie algebra. And then I have a canonical decomposition coming from my input datum that I fixed here. So I already told you, you have this maximal compact part inside U. Well, I will view I times this compact part as a subspace of GR. Then I also have my nilpotent part here. I will also view that as a part of GR. But of course, I view this as a real Lie algebra. So also here for this one, I forget the complex structure. It's a real Lie algebra now. And then the final part is just my compact part. And so as a real Lie algebra, I have this decomposition, which is called the Iwasawa decomposition. And basically, I want my choice of my dagger, or what is the same thing, the choice of my L inside G, to be compatible with this Iwasawa decomposition. So if I view my L as a real Lie subalgebra of its complexification as a real Lie algebra, I basically want that it respects this direct sum. So I want this to be the Lie algebra of, well, the intersection of L and U. I already know this is my K, this is my maximal compact part of L, but then also the other parts need to be preserved. So I basically have this decomposition where this is the intersection of L with A, and where this is the intersection of L with N. So this is the compatibility I want, and then we say that, and actually it turns out this can always be achieved. And now, once we choose one, they're all compatible. All extra choices that I can make, it doesn't really matter anymore. There's up to some isomorphism, this is unique. Okay, so the question is, why do I insist on having this Iwasawa decomposition? So basically, all choices are dictated by what Drinfeld already envisioned in the 80s, maybe early 90s. So why Iwasawa? Basically, Drinfeld insisted, well, Drinfeld showed that this Iwasawa decomposition is very natural, also in quantum group setting. So for this, I need to introduce the dual Hopstar algebra to UQU. So now I will basically try to quantize the a function algebra on the compact Lie group U. So I take matrix coefficients of finite dimensional representations. This gives me an algebra OU. I will try to quantize this one. Now, this is not so hard if I already quantized the universal enveloping algebra. Basically, I just say, I look at, I construct OQU as a subalgebra of the linear maps from UQ U to complex numbers. So this is actually a star algebra. I will not explain star structure. Let me just write for you the product. So if I have two linear functionals, since I have a coproduct, I can make a new linear functional by first applying delta and then the tensor product of the linear functionals. So this is always a star algebra. In general, it's way too big. So I look at a suitable substar algebra. And these are basically the U integral matrix coefficients of sorry, the matrix coefficients of U integral finite dimensional star representations of UQU. So here I will be not very detailed, but it turns out that if you look at finite dimensional representation theory of UQU, it basically looks exactly the same as for U itself. So you can parameterize irreducibles by the same data, by highest weight theory and dominant integral weights and that kind of stuff. And then we can say, okay, since we have this one correspondence, we'll only look at those representations here, for which the highest weight classically will integrate to a representation of U. I only take those quantizations of, I only quantize those representations, and then I look at the matrix coefficients. This will give me a quantized quantized function algebra of regular functions on U. Okay, so this, by some general theory, is again a Hopstar algebra. And the by construction, we have a pairing. So any element here, I can pair with an element here because it's given as linear functionals on this one. So I just want to be explicit and write this abstractly as some map, which takes input some quantized function and some element in the quantized enveloping algebra, and I associate to it a complex number, just by this trivial pairing, which is here. And this is, by construction, a pairing of Hopf algebras, and even a pairing of Hopf-star algebras. And so now, what is the fundamental insight of Drinfeld? That is, function algebra OQU can actually also be viewed as a quantized enveloping algebra. So, theorem. Is that if I look at this quantized function algebra of U, and for some small technical reason, which I won't go into, I take the opposite coproduct. Drinfeld tells me that this is actually, it can be viewed as the quantized enveloping algebra of A plus N. So this part of my Iwasawa decomposition of G, it's universal enveloping algebra. I can quantize by Drinfeld, namely just take this quantized function algebra with opposite coproduct. So this is very mysterious if I state it like this. I won't have time to go into the details here, but basically it just means that if you choose suitable generators here, look at their defining relations, and then let Q go to 1, you will find back this universal enveloping algebra. But you have to do this in a very careful way for it to work, but you can do it. Okay, so this is the very mysterious but very useful viewpoint of Drinfeld, that quantized function algebras are also quantized universal enveloping algebras. Yeah. Yes. Yes. So this is why I say if you choose suitable generators. So the point is that I have to make precise what it means to let Q go to 1, and I can't really do it if I take Q a fixed number. I have to view this as power series. And then it turns out that, well, if I view it as power series, I can do it in one way with one set of generators. And you're right, it will go to a commutative one. But if I do it with a different set of generators, it will go to this one. And the point is that these two viewpoints are not compatible, because if I take the one set of generators, how to say it? If I take one set of generators and I express the power series with respect to this one, I will have poles. So there will not be a suitable limit when Q goes to 1. Yeah, so this is the subtlety, which I just don't have time to go into it. But just as a kind of blanket statement, Drinfeld just says, well, conceptually, just use this one. Just use this one to view it as a quantization of this one. Yeah. It's well, yes. There's some general statements. Actually, it's more, I forget, it might even be more general. I forget now the details, but yeah, there is some very high powered structure behind this statement. Yeah, but I just use it as a shortcut, because now I can say, well, now I see an opportunity to quantize this real Lie algebra, because I already know how to quantize U. That's basically my construction I gave here. I already know how to quantize this guy, because it's just a function algebra. So if I want to quantize this real Lie algebra, I just need a way to combine the quantizations of this guy and this guy. So basically it means that we can make a quantization of the universal enveloping algebra of G as a real Lie algebra by just saying, well, I take this Iwasawa decomposition. So I have U, I have A plus and R. So this is a universal enveloping algebra of a direct sum, while it should be something like a tensor product of the universal enveloping algebra of R and universal enveloping algebra quantized of A plus NR. Of course, this will not be a tensor product just of my algebras. So this will just be a tensor product of vector spaces, and I'm not done yet. I still need to say, how do these two parts commute as algebras? And this is again something due to Drinfeld. So Drinfeld says you can let these two parts interact basically by using this this pairing tau. So OQU and UQ of A plus NR are the same thing. I can say they have to commute by this relation here. So let me just write it down to have a fixed formula, but I won't need it further in the talk. Just to show you that there is something very concrete going on. And it's something you can actually work with. So there's between UQ of U and something in UQ of A plus NR, specific commutation relation where I use these mysterious symbols, which are known as Sweeler notation, which just give you a very handy way to denote the components, the factors of the coproduct of X. Same thing for that. So if we refer back to the original Carton square, so basically we're trying to get this guy. We now are in a position where we know how to quantize this guy. Our next stop, how do we quantize this guy, the intersection? So this is where things break down a little bit. But it turns out it's still very, very interesting. So this is where I introduce Letzter co-ideals. So there is a theorem due to Letzter and based on the results and extended by many people to other contexts later on, which says that this inclusion can also be quantized. So there exists a star subalgebra UQ K inside UQU. However, it's not a Hopf-star subalgebra. So it is a left co-ideal star subalgebra, which means that if I apply my coproduct of UQU to the subalgebra, so it's not a Hopf-star subalgebra, I won't land in UQK tensor UQK, but I get the next best thing where at least one of the legs lands back in UQK. And of course, here I just say there exists. What you can make precise is that if you look at this in terms of formal power series, you really get that it's a quantization. So you really get that in the limits Q to 1, whenever you can make it precise, you actually find back the universal enveloping algebra of K. So there is some object which really behaves as if it is a quantization of UK inside UU. And it turns out it's not a Hofstadter subalgebra, but it satisfies one-sided preservation under the coproduct. So for example, if we look at UQ of SU2 that I have introduced here, you can check just by looking at the form of the coproduct, which I wrote down, that you get inside what I can view as UQ of SO2, just as the commutative star subalgebra generated by E minus E star. just by looking at how this delta of E looks like, you see that it satisfies this condition here. And so I will once more use my magic box of Drinfeld to also, so now I know by this general theory of Letzter, what is a quantization of this one? And I will use my Drinfeld magic to say, well, this one, I should be able to relate it to a subalgebra of the quantization of this one, which was my function algebra of a quantization of my function algebra of U. So what will I do? Well, let me use this blackboard. So you basically have this analog of Drinfeld's theorem for homogeneous spaces. So the idea is, well, if I have K and U, I told you I can look at this homogeneous space U mod K. And then classically, well, taking functions is contravariant, so functions on this quotient space will be given as a subalgebra of functions on U. If I want to quantize this, I need to say, what is this quantized function algebra of functions invariant under left multiplication by K? Well, recall that K was actually connected. So it means if I want to see invariance under left multiplication by K, it's enough to see infinitesimal invariance under the Lie algebra of K. And so that I can actually easily write down in quantum language, so using Hopf algebras. I just look at all F in quantized function algebra of U, such that if I infinitesimally translate F by an element of my subalgebra, it doesn't do anything. So that means that if I take my co-product of F and I apply to the first leg some element X in UQK, that's writing down in Hopf algebra language infinitesimal translate on the left by X. It shouldn't do anything, so I should find back F. But because I want things to be linear in X, I need some linear stuff here in X. And so this is co-unit of X, which is usual co-unit. So in the setting of Lie algebras, epsilon of X would be 0 for a generator. So this is just the quantization of that kind of map. So, okay, I have by some general philosophy from the classical setting that I can quantize my functions on the coset space, and then the magic of Drinfeld says that this algebra I might as well view as a quantized enveloping algebra of A0 plus N0. So this is actually not, as far as I know, explicitly in papers of Drinfeld, but there's some work of Gavarini and collaborators on this kind of Ciccoli and on this kind of stuff. So you have this same kind of Drinfeld duality for homogeneous spaces, and so now it means I have a quantization of this guy, I have a quantization of this guy, and well, they both already live in something of which I know the quantization. So now I can finally define UQ of L as being what is generated by UQ of K and UQ of A0 plus N0 being exactly this guy inside the quantized enveloping algebra of GR. Right. So now I know this is a star algebra, substar algebra of this one, and it will again still be some left. It will again be a left co-ideal star subalgebra. So now we know why it's problematic. So we don't have a delta which sends UQL into UQL tensor UQL. We only have that delta of UQL lands into UQ of GR tensor UQ of L. So there's no coproduct internal to UQL. So that would seem at the end of the story. We can't make a tensor category because we can't tensor representations of UQL. If I start with two representations of UQL, I want to apply the second one to this one, and the first one to this one, but this is a larger algebra. I can't magically extend it to something here. At least not that I know of. So now comes the magic, and I maybe have 4 minutes, I think. So what I will do is I will not have time to show how to do this stuff in the analytic framework for C-star algebras. So you can actually do this also for C-star algebras, but let me just explain the appearance of the monoidal structure on the purely algebraic side. So to end, I want to show you how you can actually get a monoidal structure. So 6. Yet there is a monoidal structure. On representations of UQL. So basically, so first, so we considered OQU as being a dual of UQU, but I didn't yet tell you if there was also something dual to the quantized enveloping algebra of K. So it turns out that there is. So there is an OQK dual to UQK. So under duality, this is a subalgebra. So this should be a quotient. So basically, we define it as being the quotient of OQU by a left ideal. And so this left ideal is basically generated by all functions which vanish on K. Which vanish at the unit of K. What am I saying? Which vanish at the unit of the homogeneous space. And so we look at all the functions which are left invariant and which vanish at the image of the unit in this quotient space. So this I can write algebraically as the intersection of the kernel of the co-unit on OQU with my space here. And so if you think about this for a little bit, you see that this makes sense as a definition of OQK from classical interpretation. But the thing is, well, this will in general only be a left ideal. So this will be a left ideal. I quotient out. I at least get a left OQU module, but it turns out that the coproduct of OQU survives. So it turns out that this is what is called the left OQU module coalgebra. So this makes sense that this is a coalgebra because its dual object is an algebra. It makes sense that it's not an algebra because its dual is not a coalgebra. It's only a co-ideal. So its dual is only a module. So it means that we have a special class of UQK modules, namely those which integrate to OQK co-modules. And if I also want to have a representation of my UQL, then I have a representation of UQK, and I also have a representation of this guy here, which was just my quantized functional algebra of cool set space. So it means that if I only am interested in modules over UQL without any analytic structure, I can look inside. To special modules where the part for UQK integrates to an OQK co-module structure. So it means I can look at things which have an OQK co-module structure, which have a left UQA0 plus N0. So this guy on the left. And the point is that there's some magic which allows to make this guy. So there's some compatibility, of course, between these two structures. And this compatibility, it turns out, by some results which are well known to some members of the audience, Takeuchi, and actually in this setting, in the analytic setting due to Chervasitu, which says that this category is actually equivalent to a category where I have OQK on both sides as co-algebras, and now I have the full functional algebra OQU here. And this guy is a monodal category because there is a way. So if I have bimodules, I know I can take balanced tensor products. If I have co-modules, it turns out there is some way to take some co-tensor products, and it turns out that this makes this category into a monodal category. And then it turns out that actually you can do this construction also in the analytic setting using von Neumann algebra language, but I won't have time for that, so I will stop here. So thank you.
Great. Well, thank you very much for a very nice talk. So are there questions first from the audience? Good. So I guess then from what, I mean, the analytic stuff you didn't have time to get into, but I mean, how does it relate to locally compact quantum groups? Or is there some generalization of locally compact quantum groups that it could fit into?
So we haven't looked at these so we haven't really looked at directly putting all of this in this framework of locally compact quantum groups. So we haven't looked at, if you start with co-ideals and locally compact quantum groups, can you do this kind of construction? So there has been some work on co-ideals by Kasprzak and Soltan, but we haven't looked at it from directly that analytic perspective. But you will get that, for example, these co-ideals, they will be co-ideals in the locally compact quantum group setting also, if you look at these specific examples. So for example, I mean, you have a C-star algebra associated to this quantized enveloping algebra, for example, and then this UQL, you can integrate it into some co-ideal of this one. But the precise correspondences we haven't really looked at yet. So there's still a lot to do there to put this in the framework or make this compatible with the framework of locally compact quantum groups.
And then what does the category, do you have any idea what the category of representations actually looks like?
Yeah,
is it the same as?
I should have said, so we don't know yet in general, but the work that I did with my student was precisely to see how it looks like in the setting of the rank 1 case. So if you look at let's say C star of a SL2R, and then you look at its quantization, then we can say precisely how this representation theory looks like. So basically in the classical setting, you have this picture. So you have basically even representations and odd representations, which go off to infinity. Then there's some magical bound here. So you're basically labeling your representations by the value of the Casimir and by the spectrum of your maximal compact subgroup, in this case, the torus. So up to a certain point, you have this kind of stuff happening to -1/4 value for the Casimir. Then you have, this extends to complementary series. So these are like your principal series. This is complementary series. Then there's something dramatic happening at 0, where you get your trivial representation, and some discrete series start to appear. So this discrete series then continue to the right. And here, there's nothing, there's a desert here. Sorry, no, there's no desert. There's at this endpoint something called limit discrete series. And then you have the same pattern where discrete series start to appear. So if you look quantum case, you do not get this picture. Basically, what happens is that your infinity will be brought to the middle, and then there will be some symmetry. So for this one, you get that the picture looks as follows. So principal series in the middle, complementary series will happen now on the left and right, and then discrete series will veer off on both sides. So this phenomenon was also kind of known when you look actually at the quantization of SL2C. So this was done in very great generality by, well, first by Yuki Arano, who looked at spherical case, and then Voigt and Juncken, who looked at general case. And you see this kind of phenomenon, which there is some extra periodicity or some extra symmetry appearing in a quantum case. And here we see, at least in rank 1, that it also happens for this real case. And so the question is what happens in the general case, and this is something that is going to take some time to figure out, I think.
But and so the representation theory is genuinely different.
It's genuinely different, yeah.
Okay. So are there any questions from the audience? Any hands raised?
And the notion of quantum homogeneous space for Yokio-Ovel?
That's a good question. I don't, because I mean, since it's not a Hopf algebra, it's not really clear which would be a quantum homogeneous space. Yeah, I don't know. That's a good question. And maybe there is something if you view it in the right framework, but it's not something obvious, I think. Yeah.
So are there any more questions? Okay, then if not, I guess we'll thank Kenny again. And so next week's talk, I guess, will be put up. It's going to be on tensor categories of some form. Yeah, so next week it's Roberto Hernandez Palomares from Texas A&M University, and he will talk about K-theoretic classification of inductive limits of fusion categories on AFC star algebras. Okay, so hopefully we'll see you all there.